Zach Vinegar, President and CTO of Gatlin Robotics, will explore how humanoid training can scale when real facilities are turned into high-fidelity simulated worlds. Automating real to sim to real will look at how environment reconstruction, synthetic data, cloud simulation, and the NVIDIA Isaac stack can help robots practice complex manipulation before hardware arrives on site. Please welcome Zach Svai.
How's it going, everybody? Awesome. Well, yeah, really excited to be here. I am the co-builder and CTO of Gatlin Robotics. So at Gatlin Robotics, we are making the next generation of cleaning robots using the latest advances in AI and humanoid robotics. So before founding Gatlin, I worked at Miso Robotics for around 8 years. And yeah, if you've heard of them, they basically make robot kitchen assistants. So, working robots that will work the deep fryer, flip burgers. I like to say that my first job out of college was flipping burgers, but really it was, making robots that flip burgers. And that's a really challenging job. It might seem simple, but there's a lot to it. Each restaurant has a different layout. Each patty is slightly different consistency. The cheese melting, can mess with the robot's kinematics, and the patty sliding onto the burger. There's just a lot of things that go into actually deploying a robot into the real world. And so I got to see that firsthand. And I got to see, the company kind of rise from working out of our garage in Pasadena to deploying these robots in restaurants all over the world. So each deployment is something new. You learn something. We deployed robots in the UK. We deployed robots in Dubai. There's a lot of different safety, compliance, everything like that. So it was really good just experiencing all that firsthand. And the stakes are pretty high in the restaurants. It's very fast-paced. A lot of dangerous amounts of hot oil flying everywhere. There's a lot of complications when you're in a restaurant. And if you make one mistake, the robot messes up one thing, you might back up the drive-thru and you have a lot of unhappy customers. The hardware is really incredible. I know we have a lot of hardware out here today, you've probably seen, that's very capable. But the question is, how can we deploy that in a safe and reliable manner? And so that's kind of what I'm going to talk to you about here today, is how we can start to use simulation and prepare ahead of time to make sure these robots are ready and reliable when they get on site, and how to make it so that our software and hardware is adaptable and the deployment is easy. So at Gatlin, we're building basically a fleet orchestration and intelligence layer that can be applied to any robot. So we fine-tune models specifically for cleaning tasks right now that could be applied to any task that can be deployed across multiple different environments, including both humanoids and mobile manipulators on a real place, or even tabletop, stationary environments as well. We also provide custom robot hardware that we add to robots to help them specialize in certain tasks. You might imagine a specific gripper or something that can use a specific tool in your environment. We're focusing on complex facility operations right now, and we like to say that our robots can do anything that a Roomba can't do. So that includes picking up trash, wiping down surfaces, dusting, anything like that. Our vision is basically crews of robots. So a robot, basically a crew of robots that would show up to a site and be able to clean and cooperate together to do various tasks, including cleaning, but potentially other tasks in the future. So, our approach pairs the humanoid hardware and potentially other hardware like floor cleaning bots with fleet orchestration software and the new intelligence layer that's coming out today. The capability and dexterity of the modern robot hardware is really incredible. And so we want to get these robots into the real world doing work. And so the question is, how do we do that in a scalable manner? We really want these robots to be doing all of the dull and dirty and dangerous jobs that they can do, so that we can free up time for people to do more of the things that they were meant to do, that they're good at, like interacting with customers, doing the creative things that people are very specialized in. And as I learned from my previous experience, it's not enough just to get robots out there. We really need a way to monitor these robots and make sure they're doing the job that we put them to, and that they learn every mistake they're making. So the reality is that every facility is pretty much a unique place, right? Like there's no two places that are the same. Even when I was working in the fast food space, you imagine that they're pretty similar, like restaurants are pretty similar, but it's not true. There's a lot of differences even there. And even more when you start to get to facilities, right? Everything is very custom, and if you wanted to have a robot consistently working in these spaces, you need to be very robust, and you need to be very adaptable to different scenarios. So the manual way of doing this before was very unskilled, right? Like let's say you want to simulate like an airport, like this is LaGuardia Airport here on the left. You're right. So, to do that, you might have to have a model designer kind of a 3D model for everything in the environment, and maybe artists designing all the different textures that you might have to put in the environment. And that's just can take weeks and weeks of work for even a single environment, which is not scalable. And then there's also the fact that we need to collect data for these robots to train on. So how do we do that in a scalable way? Because if you just have, let's say, one person teleoperating a robot, that's a 1-to-1 ratio for people's robot. That's very expensive, right? How would you do that at scale and collect enough data to train these robots? Yeah, so the labor cost for training would be way too high, if we were using this 1-to-1 ratio to train a model that would be good enough to achieve the lessons that we want with just teleop and that one. So that is really the biggest roadblock, is how do we validate each of these sites? So let's say a customer has 10 different sites, and I want to make sure the robot and the model that we train is going to work on all of them. How do we accomplish that? So our pipeline basically starts from reality. So we don't need any traditional CAD method to model up these environments. You start by walking the site one time, taking a video from even your phone or just any binocular camera, and then uploading it into our stack where we process it, take it into a 3D representation that we can then drop our robots into in the simulation environments like video Isaacson. So we do a single walkthrough, capture RGB, and then that we can turn into depth, spatial, and pose information on the camera. And the output is a dense, photorealistic simulation environment that we can then train the robots and test robots in. The speed is very fast, right? So you have a video for minutes. You can upload this video and then end up with a very realistic looking simulation environment without any of the traditional manual workflows. But photoreal is not quite enough. It's not just enough to have a static, realistic environment. They have to react to, let's say, a robot is doing manipulation tasks like picking up trash. The robots have to be physically accurate. The objects have to be physically accurate. They have to react with the same physics that a real object would in order to have these robots be able to get feedback from the simulation environment and actually test their capability. So we take that video and we run a segmentation pipeline that then isolates each of the objects and creates digital representations of the objects themselves with the correct physics and the correct friction and the correct geometry for the robot to be able to maneuver around. We then import these assets directly into NVIDIA Isaacson, and this is where we can start to add the things like physics and geometry and everything like that, everything that is needed to train the robot in the simulated environment. Another thing is that even the teleop data and the simulation data they're good starts, right? Teleop data, I think of that as the highest quality data. You're controlling the robot directly. That means the robot can directly learn from what you are controlling it to do. So I think it's like the highest quality data. Simulation data, it depends how accurate is your simulation for real life. Right? If your simulation is very far away from your life, then that data might not be worth much at all. It might actually teach the robot bad behaviors that it can only exploit in sim, but in real life, if you try to do that, it would fail. So another form of data is this egocentric data capture, which is basically a first-person view of a person doing a task. So we can also take this form of data and we can track basically the hands, the head, and then turn that into data that the robot can be trained on. And this allows us to turbocharge the data flywheel in the sense that we can now deploy many different people collecting data at the same time, people that are already very familiar with tasks and almost experts in the tasks, and then apply that to our robots. And yeah, that requires a lot lower capital because you don't need that one-to-one teleop, and you don't need the robot hardware even on site. Like let's say I want to train a robot to clean a place in Africa or something like that. Like we don't need the robot to actually be on site. We can have the robot trained from data that's being collected remotely. So we take these human demos and we retarget them to the robot's morphology, meaning, let's say a robot doesn't have hands, but it has grippers. We'll take the grasp of a person, the person grasping an object, and we'll then translate that into, okay, what if this robot was going to grab an object with its gripper? So this is a way of imitation learning, and then that also feeds into our reinforcement learning, where we can then further train the robots in simulation to do even better and at a quicker pace. Reinforcement learning allows us to learn from many different simulated environments at once. So we could kick off, let's say, 1,000 different simulation environments in parallel, and then the model is learning from them all at the same time. This allows us to really scale out and randomize the simulation so that it can be even more robust to any differences in real life. Then, this creates highly robust policies that are then ready for unpredictable variations in any new microelement. So yeah, as I was saying, you can basically kick off a number of simulations. So our simulation stack allows for cloud training. We can either use NVIDIA Rev or AWS or any other cloud provider. And that allows us to really scale, just to the number of GPUs that we're allowed to use. So we can scale to maybe thousands of GPUs at the same time, depending on our needs. So we can run these massive simulations that can then train these models and generate data very quickly. And we really want to force the robot to fail in simulation. I would much rather the robot fail and iterate that in a simulation environment than on the customer floor. So we're really pushing everything up the stack to try and eliminate a lot of the errors that we see during robot deployments beforehand. So that when the robots get on site, they work reliably and so yeah, this acts as basically a great way to regression test robots. Let's say you're training multiple different models. You can easily compare them to each other. You can compare them to other methods of manipulation. Like let's say you had a more classical approach, pick and place approach. You can compare the new model that you trained to that classical version. And so you only swap it out when it does better. So the deployment is gated on all of these checks that we have. So basically we won't deploy a new model until it's passed all of these checks that are in simulation. And then that way we can eliminate all of these errors that we might see before the models even touch any real hardware. So yeah, we're monitoring for any out of distribution edge cases. We can also throw in a lot of different randomized scenarios, agents generating different scenarios for us that might throw the robot off, and then test all those in simulation at scale, which would be insanely expensive to test in real life. And that failure data is all logged and then immediately fed back into the simulation and the model training. That way we can create a loop where the system continuously learns and improves with every introduction. So consider this kind of case study where we have a facility cleaning task, maybe a conference room, which requires some trash pickup, and then surface resets like resetting different chairs or AV systems in the conference room. The first step would be to capture the space. So we walk around with just our phone capturing video, and then that can be turned into a reconstruction of the environment and simulation. We label all of the different surfaces, table, chair, everything like that. All those assets are generated automatically. And then step 2 would be training. So once we have the simulation environment, we can then pose different scenarios. Let's say the resetter's chair, and then we can validate that yes, the chair was reset properly, and we can practice in the Isaacson bunches of ones until it succeeds. So we then run thousands of AWS simulations to ensure reliability, and the goal would be shorter integration time and massive test coverage per slot. Doing this per site, right? So this can be done at scale, all in parallel across many different sites that you might find. So why is this bad? I would say that the industry has proven that the hardware is capable, right? Like we can teleoperate these robots, we can get them to do really advanced tasks. The question is, how do we get them to do them autonomously and reliably? And so, I think I've seen a lot of great YouTube videos of robots in labs, robots doing parkour, all the dancing, all those kinds of things. But when it comes to doing actual work, I think there's a lot we can do there. But I'm starting to see a lot more of that. Like, I think there's this kind of pipeline will really unlock that capability. So physical sites can basically turn into reusable, scalable training assets that you can then use to improve your robot in many different situations. And we can turn this from pilot programs into profitable everyday utility. So yeah, my co-founder and CEO, Isaac Gresham, is also here with me today. And we'd love for you to stop by our booth, 1792. It's actually just right there. You can see it from here. And we would love to show you guys a demo of this pipeline running live. And yeah, we're really excited, looking for partner partners. If anyone is interested or knows anybody, please reach out. And after that, I'd love to open it up for any questions you guys have.
Any questions? Yes. Certain. Is there technical concepts that this works well for everything on, right? How do you segment what's possible there?
Yeah, it's a great question. So the question was, basically, is there a segment of objects or assets that this would work well for or would not work well for, right? And yeah, so deformable objects, like any type of clock, it's going to be much better to infer that from a single, all it takes right now is like a single image. But some of that can be inferred, like if you see a rug, you know it's a rug, you know that it's deformable, so agents can also determine, apply the same type of physics to the object from its memory. But yeah, it definitely works better, a lot better for rigid objects. objects that don't have a lot of transparency, like glass objects are very difficult. So anything like that, yeah.
Any other questions? Don't be shy.
Can you talk more about your segmentation pipeline? Like how manipulators, robotics?
Sure, yeah. So the question was about the segmentation pipeline. So basically the idea is in the video, you're seeing many different objects. And I guess you as a person, you would recognize if we took a scan of this room, every different object in it. So the idea is to use perception models to segment out and go, this is a separate object. What is this object? Using some of the latest AI models to recognize the objects, and then segmenting them out from the rest of the scene, subtracting out the background, that kind of thing, and then turn that, inferring the 3D structure from just a single image or maybe a couple different images of that object. Any other questions?
Wonder, do you use IR camera for study in case they're human or something like that?
Yeah, so the question is if we use IR camera. So yeah, IR cameras are very good for scenes and RGB is such things susceptible to vibrant glare, things like that. So IR can be really good at normalizing the lighting for the camera. So you might use it. We use it in applications where we're dealing a lot with depth. And depth cameras have a lot of IR sensors on them usually. And then also for the structured light, because you can shine infrared light into the structured infrared light on the environment, and then use an IR camera to read back the geometry. Based on that, that's how a lot of the real science and stereo cameras work.
Zach?
Yes. Yep.
How do you deal with the boundaries between objects in your segmentation?
Yeah, so how do we deal with boundaries? So that's a good question, yeah. And a lot of that is the real challenge. Like let's say two objects very blend, like let's say you were doing your bed. Do you want to segment out the pillows or the sheets? Right, that's a really good question. And that is one of the big challenges. And I think it depends on the use case. So for example, if we did want to manipulate on a bed, because if we do want to manipulate the sheets, we would have to kind of maybe focus it a little bit and say like, actually I want to manipulate the sheets and the pillows instead of just the mat as a whole. And so in that sense, we can dig in a little bit further into that specific area. Versus in some use cases, you might be fine just saying like, this is one object as a whole.
And we have a repeater.
Sorry. I guess my understanding of the status quo coming into this presentation was there would be someone like a technical artist who would generate a scene pretty procedurally and then get the dimensionality, like information about the scene to make sure it's accurate. How do you measure success of this pipeline? And maybe both on the real precision and this on the real.
That's a good question, yeah. So we both measure in terms of like how accurately can it represent the physical space, like in terms of the dimensions, so like checking the dimensions of objects, the dimensions of randomness, colors, matching the colors, the texture, not necessarily texture, but the physics, like the mass and friction. So seeing how the objects will react to the robot manipulating them in real life versus in simulation, and then comparing how they react and either tuning from there or, so we have basically agents that are doing that for us, so trying to iterate and make those agents better over time, like feedback, like, this object actually weighs a lot more, or this object has a lot more friction than the other.
Anyone else? Okay, you can find Zach at booth 1792. Zach, thank you for an excellent presentation.
Thank you guys. Really appreciate it.